All right, guys, so linear approximations. Basically what we're looking at here is, let's say I have a function and I've got this blue line as my original function. What we're talking about when we say a linear approximation is, remember, linear just means straight line and approximate means close to. So what we're trying to do is say this point on both graphs, this point on my tangent line is exactly the same point on my original function. So what if I am looking at, what if it's really hard to find the value on the original function? Well, as I get closer and closer to this point on both graphs, so as I get closer to this value on my original function, my tangent line function gets closer to that same value. So instead of looking at what happens to my y value for my original function, what if I just look at the y value of my tangent line as I get closer? Because it's a lot easier to find a value on a tangent straight line than it is to find a y value of a crazy ugly curve. So we use that. What we say is we find the tangent line at a certain point. And we say, okay, as I get closer to that point on my tangent line, then my value should be the same as it is on my original function. It's not going to be the same anywhere else, but it's going to be the same really close to that specific point. So for example, let's go ahead and do one right here. It says to use the tangent line at x equals 4 to approximate f of 4.1. So it gives me a function and says, let's find the tangent line near at x equals 4. And let's use that to approximate my value of 4.1 instead of actually plugging in 4.1. Now, plugging in 4.1 with a calculator, that's not hard to do, but doing it by hand sometimes is an ugly mess. So let's go ahead and work through that. If I take, to find the tangent line, I need a point. So when x equals 4, I need to know my y value. So I go ahead and plug in 4. So 4 to the 1/2. Now remember, 1/2 is just the square root. So that's basically saying what's the square root of 4 minus 4 to the 3rd, but you take the square root of it, plus 7. So the square root of 4 is just 2, minus 4 cubed. Well, 4 cubed is 64. The square root of 64 is 8, plus 7. So 2 minus 8 is going to be -6, plus 7. This basically becomes 1. So when x equals 4, my y value is 1. So the point I'm going to use is 4, 1. And I also need the slope. So remember, I need the slope at this point. So I'm going to have to take the derivative of my original function. So let's go ahead and clean some of this up. Just get it out of the way so that I can work in the same area here. So let's take the derivative of f of x. So that f prime of x is going to equal x to the 1/2 becomes 1/2 x to the -1/2 minus 3/2 x raised to the 1/2 plus 7. Oh, well, no, that plus 7 goes away. That the derivative of 7 is nothing. So there shouldn't be anything there. And if I wanted to rewrite this right now, this would just become, oh, where'd my pen go? F prime of x equals 1 over 2 root x minus 3/2 x to the 1/2 is just 3/2 times the root of x. So when it wants us to find at x equals 4, so I need the slope at this point. So f prime of 4 equals 1 over 2 root 4 minus 3 root 4 over 2, which just becomes 1 over 4 because root 4 is 2, minus 3 And the root 4 is 2 over 2 is just going to cancel out. So it's just 1/4 minus 3, which is either negative 11/12 or it's negative what, 2.75. So that's my slope. That's going to be my slope at this point. So my tangent line is going to be y minus y1, which is 1, equals my slope, negative 2.75, times x minus x1, which is 4. So this is, well, we better add 1 to both sides. So negative 2.75 times x minus 4 plus 1. So here's my tangent line. Now, my tangent line is what I'm going to use to approximate this 4.1. So instead of plugging 4.1 into my function, because it's really close to 4, I'm going to plug 4.1 into my tangent line. Because when I do that, I get y equals negative 2.75. 4.1, when I plug it in, 4.1 minus 4 is just 0.1. And then I'm going to add 1. So let's go ahead and put that in. Negative 2.75 times 0.1. And then I'm going, whoops, I don't want to do that in my y equals. Negative 2.75 times 0.1 plus 1 is going to equal 0.725. So my y value, when x is 4.1, my y value is, I'm not going to put it equals, I better put an approximately 0.725. So that's my approximation. When x is 4.1, y is approximately 0.725. And if I wanted to figure out exactly what y was, we could plug 4.1 into this original equation. We could do 4.1 raised to the 0.5 minus 4.1 raised to the 3/2 plus 7 and get an exact answer. It's 0.722. So what y actually is 0.7229. And we're approximating that it's 0.725. Okay. So what we call that is an over approximation, because we are a little bit bigger than our actual y value. And you know that that's going to happen because our tangent line right here is over our original function. Our original function is this blue line, and our tangent line is always a little bit bigger than that blue line. And we know that because the blue line is concave down. So that means my approximations are all going to be over approximations because my function is concave down. If my function was concave up, my tangent line would be below my function. So all of my approximations would be under approximations. They would be low instead of high. Okay. Moving on to, let's go ahead and look at another example here. So this is just the exact same thing, the equation for the tangent line at c, f of c. I just want you to see this function. But if you look at it, y minus f of c, well, f of c, that's just like saying y1, equals f prime of c. Well, that's just a slope. And x minus c, that's just x minus x1. So this is just our normal tangent line formula, just rewritten in another way. Okay, so finding the tangent line approximation at the point 0,3. So we're going to do the same thing, but then it wants us to use a table to compare the y values to the original function. So if my original function is f of x equals 3 plus sine of x, what I want to do is find our approximate. Now it already gives me the point 0,3, so I don't even have to plug in the 0 to get the 3. It gives me my point. So now I just need my slope because I got to come up with my tangent line. So my slope of this original, my f prime of x, is going to equal, well, the slope, my derivative, f prime, this goes away. Sine of x just becomes cosine of x. So here's my function to get my slope, and then I'm looking at 0. So f prime of 0 equals cosine of 0. And if you think about your unit circle, the x value at 0 is 1. So my slope is going to be 1. So when I plug that in, I get y minus y1, my 3, is equal to my slope 1 times x minus 0. So when I add 3 to both sides, I just get, well, I really don't need to write all of that, but y equals x plus 3. Because when I distribute that, the 0 is going to go away. So my tangent line that I'm going to use, the function is y equals x plus 3. That's my tangent line. And instead of plugging in at the exact, into my original function, I'm going to go ahead and plug things into, I'm going to use my tangent line to approximate, okay? So when I use my table, what I'm looking at is I'm comparing these two functions around when x is equal to 0. So I have my original function right here, and I have my tangent line that I'm going to approximate. But I can't approximate everywhere because look at what happens. If I go ahead and let's go to y equals, and let's plug in 3 plus sine of x. And then we're also going to plug in x plus 3. All right. So when I look at the table for these two functions, when I plug in 0, well, actually, let's change this. Right now, sometimes when you go to the table and it's already plugged numbers in for you, if you want to be able to plug in whatever numbers you want, you do second table set, and you want it to ask you the independent variable. So now when I go to my table, it's not going to give me anything until I plug something in. So if I plug in 0, then my original function is going to give me 3, and my tangent line is going to give me 3, which is what we wanted. We wanted to approximate what happens around 0 for when I use this tangent line to get that approximation. So if I look at a little bit smaller than 0, like if I look at negative 0.1 and hit enter, my answers are still pretty close together. And same if I look at 0.1. If I look at a little bit bigger than 0, my answers are still pretty close to each other. But if I get too far away from 0, remember this was a linear approximation around the point x0, that 0, 3. So what happens if I start plugging in like 1, look at what happens. My original function is 3.84, but my linear approximation function is 4. And if I get further away, if I plug in 3, my numbers really start to get further apart, okay? So that is only a good approximation when I'm near 0. The further I get from 0, the further my numbers, my y values get, which makes sense. If you look at the graphs that we used before, as I get further and further away from this original point, my tangent line and my function are going to get further apart. Okay, so that's only a good approximation at that specific point. So a couple of reminders before we do the next problem. In fact, we haven't really looked at this in a lot of detail, but just our differential formulas. If u and v are differentiable, then the derivative of our constant u is just the constant times the derivative of u, okay? The sum and difference is the same. The derivative of a function plus another function is just the derivative of u plus the derivative of v. So in the past, we've usually just written this as like the derivative. What's the derivative? d dx of x. It's just 1. So if I times that dx to both sides, I end up with the derivative of the d of x is equal to 1 of dx, Okay, so looking at kind of how that plays out, we're just moving this d dx, we're treating that like d divided by dx. So my derivative before, the derivative of y equals x squared, you would have just said is dy dx equals 2x, right? You take the derivative of the left and the derivative of the right, you'd say dy dx equals 2x. Well, when we write it as a differential, a lot of times we just multiply that dx to the other side. So we would say dy is equal to dx, or 2x dx. We just multiply that dx to the other side. Same thing here. Y equals 2 sine of x is just dy dx equals 2 cosine of x. But if we were writing it in differential form, we would say dy equals 2 cosine x dx. We would put the dx on the other side. Let's do one more. Y equals x cosine x. We would say dy dx equals, we have to use the product rule here. So we would say the derivative of x is 1 multiplied by cosine of x, plus the derivative of cosine x is actually negative sine of x times the original x. And when I write this, negative sine x multiplied by x, I usually put the negative in front. So let's actually rewrite that. Dy dx equals the cosine of x, and I'm going to put the negative x in front with the sine x. And then to write it as a differential, I'm just going to multiply dx by that whole side. So I'd say dy equals the cosine of x minus x sine of x dx. Now, what this dy and this dx means when they're by themselves, this dx right here means an infinitely small change in x. Remember, dx means if I change x just a little bit, then, and I times that by 2x, I'm going to get a little infinitely small change in y. So that's what the dy and the dx mean when they're by themselves and not written like dy dx. Okay, so applying that to a problem here. It wants us to use a linear approximation to approximate this value right here. So we're going to ignore this big function up here at the top for just a minute. This is just basically giving us another form, another way to write the linear approximation. But dealing with just this problem down below, using the linear approximation to approximate the square root of 16.2. Well, I could plug the square root of 16.2 into my calculator, but if I don't have my calculator, then I can say that, well, this kind of looks like the square root of x function, right? But instead of x, I'm going to plug in, instead of 16.2, I'm going to plug in something that I know the square root of. I'm going to use the point 16. Because I know that the square root of 16 is 4. So if my function is y equals square root of x, I know that I get 4 when I plug in 16. Okay, so that gives me my point. I know the square root of 16 is 4. So now we got to take the derivative of this function right here. So again, y prime equals, we've done this. If I'm taking the derivative of, y equals x to the half. So y prime equals 1/2 x to the negative half, which equals 1 over 2 root x. Okay, we've done this derivative a whole bunch of times. Hopefully we're getting faster at that. So what I want to know is, what is the slope at this point right here? What is my slope when x is equal to 16? So if I'm looking for y prime at 16, I'm going to plug in 1 over 2 root 16, which just equals 1 over 2 times 4, which equals 1 over 8. Okay, so my tangent line that I'm going to use for my linear approximation, I've got my point 16.4. That's close to 16.2. And my slope at that root 16 is 1/8. So I go ahead and use y minus my y1, which was 4, is going to equal 1/8 x minus my input, which was 16. Okay, so basically y is going to equal 1/8 x minus 16 plus 4. So if this is my tangent line that I'm going to use to approximate, instead of 16, I'm going to approximate 16.2. So if I were to plug a 16.2 in right there, maybe let's change the color a little bit. Let's plug in a 16.2. I'm going to get y equals 1/8 times 16.2 minus 16 plus 4, which is just 1/8 times 0.2 plus 4. 1/8 times 0.2, we can go ahead and plug that in. 1/8 times 0.2. And then when I add 4, I get 4.025. So my y is approximately 4.025. Now I can plug it in and find out exactly what it would be because I have a calculator. I can say, all right, what's the square root of 16.2? Whoops, let's make that a 1, not a 0. And it tells me 4.0249. So y is actually 4.0249, blah, 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 blah. But it's approximately 4.025. So my approximation is an over approximation. It's a little bit higher than my actual y value, which makes sense because if you think about the function, this is a root function, and any tangent line is going to be above. We're going to pretend that that was a tangent line. Look, we'll just make this thicker. Any tangent line, my tangent line's above my actual function, so my approximation is going to be a little bit big, okay? Now, you could do the same thing with 26.1, but remember, this is only a good approximation near 16. This is not a good approximation near 26.1. This only works near 16. So to do this for 26.1, I've got to pick a new value that's closer to 26.1 that you know the square root of. So if it was me, I would choose square root of 25 because I know that the square root of 25 is 5. So I could say my y equals square root of x. I could still say 5 equals the square root of 25. So my point is 25, 5. But before I can't just plug that into this 1/8 x minus 16. I have to find a new linear function. So here's my point. I would just need to find the slope using this point instead of using the 16. So you can go ahead and work through that problem on your own. All right, so applying this to an AP question, kind of like the last one that we did, it gives us a table and then it gives us a whole bunch of information that we're not even going to get into today because part A, you don't even know how to do that. We haven't done integrals yet, and this wants you to take the integral of a point from 0 to 1.5 of the derivative function here. So we can't even do that yet. But we can do part B. We can write an equation of a line tangent to the graph of f at a point where x equals 1. So what it's asking us to do is approximate near x equals 1. What would the value be of 1.2? So we're going to find a linear approximation. So to do that, we need a tangent line, which means I need a point and I need a slope. Okay, well, it tells me that the point it wants me to use is x equals 1. So when x is equal to 1, my f of x is -4. So the point that I'm going to use is 1, -4. And I'm going to approximate at 1.2, which means I need to find the derivative. I need the slope at this same point. When x is equal to 1, I need the slope, which f prime of x gives me, right? F prime of 1 gives me the slope at 1. So f prime of 1 is 5. So I've got a point and I've got my slope. My slope is 5 at f prime of 1. So we go ahead and write our tangent line. Let's give ourselves some room down here. So I'm going to say y minus y1, which was, what was our y1? Negative 4. So y minus negative 4 equals the slope, which was 5, times x minus x1, which was 1. So y plus 4 equals 5 times x minus 1. And when I minus 4 from both sides, my tangent line is y equals 5 times x minus 1 minus 4. Okay, so here's my tangent line. Here's my point right here. And here's my slope at that point. So now I need to take a linear approximation. So I've got y equals 5 times x minus 1 minus 4. And it wants me to approximate 1.2. So I'm going to plug in 5 times 1.2 minus 1 minus 4. So I get 5 times 0.2 minus 4. Well, 5 times 0.2 is just 1 minus 4 is going to equal negative 3. So y is approximately negative 3. All right. Now remember, it's not exactly 3. It's approximately negative 3. And I could check that. Again, I could go to y equals, or it's not even y equals. We can just go to our regular function. I guess it doesn't give us a function to plug in. So we can't actually plug it in and check our work. And the way that they're going to grade this, the grading scale's covered up right here. But what it's going to do is it's going to give you 1 point right there for having the tangent line. It's going to give you 1 point for having the linear approximation. So again, maybe we should use a different color. This is going to be 1 point right here. This is going to be 1 point right here. And I'm guessing, let's see, 9 points. It might give you a point for finding this slope right here as well. That would probably be your other point, that at f prime of 1, the slope is 5. So recognizing that might give you another point. Actually, you know what? That's not true. Finish reading the question, Mr. Reed. Is this approximation greater than or less than the actual value, and give a reason? Okay, so we're not going to get a point for our tangent line. We're going to get 1 point for finding the approximation. And then it asks us 2 more questions. Is this approximation, is this negative 3 an over approximation or an under? Is it greater than or less than the actual value? Now, the way that you're going to have to figure that out is, remember, we're looking to find out if our original function, so if our original function was concave down, our tangent line would be an over approximation. If the original function was concave up, our tangent line would be an under. So there's a couple of places that we're looking, and the easiest is if we know something about the second derivative, which we do right here. There it is. F double prime of x is greater than 0. So our second derivative tells us concavity. Okay? It tells us concavity about our first original function. So if our second derivative is greater than 0, then we know that this is concave up. If our second derivative is greater than 0, our original function is concave up. Now, since we're between these 2 points, then it says that our second derivative is greater than 0. So what we would say is that our original function is concave up. So we have a under approximation, right? Our tangent line is under. So the way I would answer this, I guess I'm out of room. I keep trying to scroll and I can't. This is an under approximation because our original function is concave up at 1.2. Our original function is concave up at 1.2 since our f double prime is greater than 0 at 1.2. So what you would actually get, you would get a point for saying, here's my approximation. You would get another point for saying it's an under, it's lower than the actual value. And you would get a third point for this explanation right here. You would have to give them a reason why you know that that's an under approximation. So that would get you your 3 points. You would actually have to write out the reasoning, and you'd get a point for the value and a point for saying that it's under an under approximation.